Chapter 18 is on an extension of least squares to nonlinear least squares. We'll explain that momentarily. It's a very interesting topic. So we'll start with the idea of nonlinear equations and nonlinear least squares. So a set of nonlinear equations looks something like this. I have some variables, x1 through xn, and those are scalar variables, and I think of them all together as simply a vector x. And then I have a set of equations, like fi of these variables is equal to 0, and I have m of those. Now, this is like if f is affine, this becomes a set of linear equations. So we refer to fi of x equals 0 as the ith equation. And if I choose an x, then fi of x is the ith residual. Residual is usually something like an error, or it's the amount by which something fails to hold. And in this case, if fi of x is, with the residual, it tells you if it's 0, that means that equation holds. If it's, 0.003, that means it almost holds. And if it's minus 0.0001, it means it also almost holds. Okay. So we can write this system of equations up here in a very compact format. This is f of x equals 0. And here, f is a function that maps Rn to Rm, and what that means is it takes in an n vector or n scalar arguments x1 through xn, and it returns an m vector, and these are the residuals, the m residuals. So, and sometimes you can write it this way: it's f of x equals f1 of x up to fm of x. Now, if f is affine, the system of equations f of x equals 0 is just a set of linear equations. And we'll refer to this set of nonlinear equations following the nomenclature we use for linear equations. We're going to refer to these as overdetermined if there are more equations than variables. It's going to be underdetermined if there are fewer variables, m, than if there's fewer equations than variables. So m is the number of equations, n is the number of variables, and square if they're exactly equal. So we're going to follow the same nomenclature we use for systems of linear equations. Nonlinear least squares is the following problem. It's find a vector x hat that minimizes the following: simply norm f of x squared. And that's f1 of x squared plus, it's basically the sum of the squares of the residuals in an equation. Okay. Now, this includes the problem of solving the equation, simply the nonlinear equations f of x equals 0. That's a special case. Because if there is an x for which f of x equals 0, then for sure that x minimizes this, because then the norm squared is 0. And norm squareds don't come any smaller than 0, so that means that no other point x could beat it. Okay, so this is just a special case. But like linear least squares, it's super useful on its own. In other words, even when there is no x for which f of x equals 0, this finds you something that kind of gives you a nice compromise that minimizes the sum of the squares of the residuals. So very similar to linear least squares. But this is the nonlinear least squares problem. And so we have these functions, and the goal is simply to minimize basically the norm squared of f of x, where f of x is this mapping from Rn to Rm. So let's look at the optimality condition, and we'll get that from calculus. And there'll be a few things I'm going to say about that. So the first is that the gradient of the calculus tells us that if I have a function of many variables, if a point x is optimal, then the gradient vanishes at that point. By the way, if that weren't the case, you could just step in in one of the directions in order a very small amount along one of the axes to actually find a point that has slightly smaller objective value, in this case the norm squared of f of x. Now, also, you should remember that there are points where the gradient vanishes, but they don't minimize the function. For example, they could maximize the function. Okay. So, as I said, points can satisfy this and not be optimal. I think one way to say points that satisfy this are sometimes called stationary, because Yep, that's what it means. If stationary means that if you move a little bit in any direction, the function doesn't decrease fast, right? It might decrease a very, very small amount, but that's stationary. Um, and the gradient of the norm squared of f of x, we could write this out. And by the way, this is a formula completely analogous to what you'd see in the scalar case. I'm not going to derive it here. You'll find that in the book to see how that's derived. But it turns out that this thing is exactly 2 times df of x hat transpose times f of x equals 0. Okay, so that is the condition. And look, that would be the same if f were a scalar function and I said, what's the condition that this is minimized? Well, we'd take the gradient of this thing, or well, in this case, just the derivative, and we'd get 2 f prime of x times f of x here is what we'd get. And that would be, we'd want that to be 0 if that's minimized. Now, in the scalar case, it's pretty simple. It's either f of x is 0 or f prime of x is 0, and this kind of makes sense. Okay, so this is the matrix analog of this scalar equation here. Right. Of course, you don't see transposes here because these are just scalars. All right. Now, this matrix df of x, df evaluated x hat, that's the derivative or Jacobian matrix of the function f. And that's simply the matrix of partial derivatives. So the ij entry is the partial derivative of fi with respect to the variable xj, and all evaluated at x hat. Okay, now this condition, if f is affine, then this condition reduces exactly to the normal equations you see in normal in linear least squares, so-called linear least squares. Oh, I should say that when we're talking about nonlinear least squares, we refer to least squares as linear least squares to help distinguish. Now we get to an admission. So here's the admission. It turns out solving nonlinear equations is like basically super hard. So in other words, simply, if I give you even things with, as few as 10 or 20 variables, and it turns out it's just insanely difficult to actually minimize the norm squared of f of x. So in particular, it's much harder than solving linear equations. We can solve linear equations easily with thousands of variables, thousands of equations, no problem, and we will always get exactly the solution, period. That's least squares, and we'll get it, by the way, super fast. Nonlinear equations, nonlinear least squares is a different story. And in fact, the following is even hard. If I give you a nonlinear function f, and I simply say, does there exist a solution? So just find me an x for which f of x equals 0. Even that problem is hard. Now, when I say it's hard, and what I am is I'm just interpreting what it means to solve the problem. It means find a point where the norm squared is smaller than any other point. That is actually hard to do. But turns out there's still methods that do very well in a practical sense. And we'll use so-called heuristic algorithms. Now, a heuristic algorithm is one that it's not always guaranteed to work. Work in the sense of actually finding the actual point that minimizes. But they often work very well in practice. By the way, even when they fail to find a point that truly minimizes the objective function, they can find a point that is quite good. And the truth is often they do actually solve the problem. But we've encountered this before. So the k-means algorithm is a heuristic for solving the quadratic clustering problem. And what that means is that the k-means algorithm, when you run it, it is absolutely not guaranteed to find the point that minimizes the objective in the k-means problem. Okay, so, and we even saw that was the case because we'd run k-means a couple of times, and we would indeed find that sometimes it finds, a point with one value, and then later it finds a point with a lower value, meaning that in the first case, that was not optimal, period. It's also likely that the one you found later wasn't optimal. So nevertheless, heuristics like this still work very, very well in practice, right? Hasn't stopped the use of k-means. K-means is used all over the world in hundreds of applications and areas all the time, and it works just fine. Thank you. in a practical sense, right? So the only thing I would say about that is if someone says, have you really minimized that? And if you're in a court of law or there's, I don't know, mathematicians hanging around or something like that, then your answer would have to be, okay, no, technically, I don't know that I've actually minimized it. But boy, that's a pretty good, that's pretty good clustering, wouldn't you say? So, so that's the same idea with, it's exactly the same for nonlinear equations, right? That generally we just use a heuristic, and the only thing that happens there is you can't say that for sure that is actually the point that minimizes the norm squared of f of x. We're now going to look at a couple of examples just to see what do nonlinear least squares equations look like. What are some nonlinear equations you might want to solve, and so on. And by the way, later we'll describe these heuristic methods for solving the nonlinear least squares problem, which includes a special case solving nonlinear least squares. But let's right now look just at some examples. Okay, here's one, is computing equilibrium points. This comes up in a ton of fields, all over it comes up. And the general setting is that you've got a bunch of variables, n of them. And then usually what you have is some kind of equilibrium condition. And the equilibrium condition, generally speaking, means that, sort of consumption matches production. I mean, it can depend what it is. So these are called, that's generally an equilibrium. An equilibrium point is when that happens. So I'll look at two examples, one from economics, one from chemistry. So in economics, you look at, you have the idea of equilibrium prices. And so what that is I have a function, S, and what it does is we vary the prices of n goods. That's the vector P. S of P tells you what will be the supply of those goods if the prices are P, right? And so, this is it's kind of clear intuitively how that might work. That, for example, as you increase the price, if you increase the price of some good, then more people are going to manufacture it or supply it. And so the supply will go up. That's roughly the idea. We also have the demand. The demand will kind of go the other way, right? That if I have a demand function and I increase the supply of a good, presumably its demand will go down. Now, we've already seen in the price elasticity matrix the idea that when you increase one price, it could easily be that the demand for other things, other goods, can either go up or go down, right? So depending on whether it's a substitute or something, or a correlate, or I forget what they call it. Okay. All right, so back to our problem. These are our functions, the supply function and the demand function. And here's the goal. Find a set of prices for which the supply balances the demand. That's the idea. Okay, so this is a very classic problem. And what we'll do is we'll take f of p to be s of p minus d of p. That's I think some people call that the excess supply or something. I don't remember. Anyway, when f of p is 0, that means that the prices are such that the supply exactly balances the demand. Okay, so that's called an equilibrium price. A set of equilibrium prices. It's an equilibrium price vector. Okay, so that's one example of solving nonlinear equations. I should add something that if the supply and demand functions are both affine, this is a set of linear equations, and we can solve it. Well, we can solve it exactly in that case using the methods previously in the course. Okay, next example, which, although on the face of it looks radically different, is actually kind of the same example, but here it is. So in chemical equilibrium, what I have is I have an n vector of concentrations C of n different species, right? So these could species in some chemical solution, let's say. Then what I have is I have if I have various reactions that some reactions consume the species, others generate additional species, right? So these are the reactants and products. And they are given by reaction rates. And those are given this way. So capital C of little c, that tells you the consumption of the species as a function of the concentrations. So that's how that works. So usually if the concentration of a reactant goes up, then it's gonna consume more. More of it will be consumed because there's a reaction that consumes it or something like that. Now we also have G of C. That's the generation of species. These are essentially the reactant products. So that says that as a function of the concentrations, this tells you the rate at which the species are created, right? And that means that there are that means what's the rate at which the reaction in which these things are on the right-hand side. They are products, not reactants. Okay, so that's the idea. And then what we'll do is we'll take what we would like to do is find me concentrations of these species in this solution or whatever it is, so that the consumption is exactly equal to the generation. And what that means is that the reactants and products are balanced. You may still have, or you will have chemical reactions going on, but what will happen is at equilibrium, the amount of, whatever, some hydrogen ion being consumed per second is going to exactly balance the amount of hydrogen ion being generated as a product every second, due to multiple reactions. So that's the idea, and that's referred to as a chemical equilibrium. And you can check how does that vary with external things that we're not counting here, like temperature or something like that, pressure. Okay, so and to do that, we'll set that up as f of c is equal to the consumption minus the generation. And so when f of c is 0, that means you have chemical equilibrium. So that's the idea. So these are just computing equilibrium points, are generally nonlinear equations, systems of nonlinear equations. By the way, very typically with an equal number with m and n equal to each other. So these are typically square systems. Another example, it comes up in a lot of areas, but it's really part of GPS, Global Positioning System. So here I have a 3-vector x, and that's a position in 3 dimensions. And your job is to estimate it, like what is x? And what we have is actually so-called range measurements. So of course I'll draw in 2D, but here's x, and you might have a beacon or something like that, or satellite, whatever you like. It's here. And then what we measure is actually the distance. So we measure the distance, right? So here's A1 and here's A2, this point. And so what we know is the distance. Now, then the question is, given a set of distances, and I should say, we get the distance but with a noise. So VI is a noise that we don't know. And it's just measurement error. Okay. And so the idea is from these distance measurements, they're called range measurements, right? Because the range is like the distance from you to some target or from you to some beacon or something like that. So given these noisy range measurements, your job is to figure out what x is. Okay. Now, what least squares location estimation does is it says these things here are essentially it's going to sum we're going to minimize the sum of vi squared. Okay, and this is just so this is so what we're going to do here is we're going to choose x to minimize this. Rho I is the measured range or distance, and this is of course a function of x. It is definitely not affine. And we'll want to minimize this, and that is a nonlinear least squares. That's nonlinear least squares, right? And a variation on this actually is kind of what's used in GPS, the Global Positioning System. There's a couple of tricks in GPS or variations on this that are not in my formulation here. One is that in addition, when you get your distance to a satellite, there's an additional offset term which depends on how far your clock is from the true clock, right? So unless you happen to have an atomic clock with you, very few people do. So there's an additional variable there, but otherwise it's basically this. And in fact, this is kind of what's used for GPS. Actually, really what's used for GPS is a combination of this and the Kalman filtering or state estimation that we looked at in the previous lecture. But this is the essential idea.